Before collecting data, researchers often want to determine how large their sample needs to be. Choosing the correct sample size is important because it affects both the accuracy of the results and the resources required to collect the data. Planning sample size helps researchers budget time, money, and effort while ensuring that the study achieves the desired level of precision. When constructing confidence intervals, the margin of error plays a key role. The margin of error depends on three main factors: the critical value from the probability distribution, the variability of the data, and the sample size. By rearranging the formula for the margin of error, we can solve for the sample size needed to achieve a desired level of precision. First, consider the situation where we want to estimate a population mean. If the population standard deviation sigma is known or can be estimated from previous research, we can determine the required sample size using a simple formula. The sample size n equals the quantity z to alpha over 2 times sigma divided by the desired margin of error, all squared. To understand where this formula comes from, we begin with the expression for the margin of error in a confidence interval for a mean. The margin of error equals the critical value z alpha over 2 multiplied by the population standard deviation divided by the square root of the sample size. We can rearrange this formula to solve for the sample size. First, divide both sides of the equation by the critical value z alpha over 2. This gives the margin of error divided by the critical value on the left side and sigma divided by the square root of n on the right side. Next, we continue rearranging the equation by dividing both sides by sigma. This leaves the margin of error divided by the product of the critical value and sigma equal to 1 over the square root of n. Finally, by squaring both sides of the equation and solving for n, we obtain the formula for the required sample size. The result shows that the sample size equals the quantity z alpha over 2 times sigma divided by the margin of error, all squared. In practice, the population standard deviation sigma is usually unknown. When this happens, researchers often use an estimate from a pilot study or from previous research conducted on a similar population. Another practical point is that we always round the sample size up to the next whole number, since sampling a fraction of a person is impossible, and rounding down would produce a larger margin of error than desired. Now let us consider the sample size needed to estimate a population proportion. In this case, the formula for the required sample size depends on the desired margin of error, the critical value, and a preliminary estimate of the population proportion. The formula states that the sample size equals the square of the critical value divided by the margin of error, multiplied by p star times 1 minus p star. This formula comes from rearranging the margin of error for a confidence interval for a proportion. The margin of error equals the critical value times the square root of p star times 1 minus p star divided by the sample size. To solve for the sample size, we first divide both sides by the critical value. This gives the margin of error divided by the critical value equal to the square root of p star times 1 minus p star divided by n. Next, we square both sides of the equation to eliminate the square root. This gives the margin of error squared and divided by the square of the critical value equal to p star times 1 minus p star divided by the sample size. Finally, rearranging the equation and solving for n produces the formula for the required sample size. The result is that n equals the square of the critical value times p star times 1 minus p star divided by the margin of error squared. An important practical question is how to choose the value of p star. If previous studies or pilot data are available, researchers can use that estimate. If no prior estimate exists, the safest approach is to use p star equal to 0.5. This value produces the largest possible sample size and therefore guarantees that the desired margin of error will be achieved. Let us now look at an example involving blood pressure reduction. Suppose a medical researcher wants to estimate the average reduction in systolic blood pressure from a new medication. The researcher wants the estimate to be within 2 millimeters of mercury of the true mean at the 95% confidence level. Previous studies suggest that the standard deviation is about 8 millimeters of mercury. Using the sample size formula, we substitute the values for the critical value, the standard deviation, and the desired margin of error. With a 95% confidence level, the critical value is 1.96. Substituting into the formula gives the sample size equal to 1.96 times 8 divided by 2, all squared. Carrying out the calculation gives a value of approximately 61.5. Because we must use a whole number and rounding down would produce too small a sample, we round up to 62. Therefore, at least 62 participants are needed to achieve the desired precision. Next, consider an example involving a survey of smoking behavior. Public health officials want to estimate the proportion of adults in a city who smoke cigarettes with a margin of error of plus or minus 0.04 at 95% confidence. A previous survey suggested that the smoking rate is about 30%. Using the formula for proportions, we substitute the critical value, 1.96, the margin of error, 0.04, and the preliminary estimate T star equal to 0.30. Performing the calculation gives a required sample size of approximately 504. Since we must round up to ensure the desired precision, the official should survey at least 505 individuals. If no prior estimate of the smoking rate were available, using P star equal to 0.5 would produce a larger sample size requirement of about 601 people. Finally, it is helpful to understand how the margin of error changes as the sample size increases. The margin of error decreases in proportion to 1 over the square root of the sample size. This means that increasing the sample size reduces the margin of error, but the improvement becomes smaller and smaller as the sample size grows. The graph shown here illustrates the relationship between sample size and margin of error. Notice that the margin of error decreases as the sample size increases, but not at a constant rate. In fact, quadrupling the sample size cuts the margin of error in half. This relationship highlights an important practical point. Achieving much smaller margins of error requires dramatically larger samples.